Welcome back to Designing AI-Driven Personalized Learning Environments course. We'll talk about conditional property table. That is the second property of Bayesian network. We saw Bayesian network is dynamic acyclic graph, and also we said that's a big property of conditional property table. Let's go back to our original the dynamic Bayesian network. Assume the value of the nodes as Boolean, yes or no, slept or not, meeting, yes or no. Class is actually given not attended because it's just we say that not attended, yes or no, and video watching is yes or no. For node yes, the probability of values to represent will include s equal to 1 or s equal to 0. For example, I gave out of 15 classes, 2 classes I might have slept, other classes I will not sleep. I will after 15, 13 times I wouldn't sleep, 2 times I might have slept. Our meeting is 4 times or 15, 11 times, something like that. So we have probability values emerging out of it. For node C, we might need only 2 probabilities, right? So yes or no. But node C is a conditional node. So what we need is we need a 4 combination of possibilities. For example, for node C, we need to know what is S and M, the both nodes, which is what are child nodes, both the parent nodes included. For example, s equal to 1, m equal to 1, s equal to 0, m equal to 0, or s equal to 1 and m is 0, or m equal to 0 or s equal to 1. All these combinations possible. So node C will be represented by the 4 nodes, and node V will be represented only by the node C, that is 1 or 0. Okay, so it is clear, right, how these values are represented. So this has only 2 values, probability of s equal to 1 or probability of s equal to 0, probability of m equal to 1 or probability of m equal to 0. Similarly, probability of V given C naught equal to 1, probability of given C naught equal to 0, whatsoever. So the 2 values would come into picture. Similarly, C naught will have 4 probabilities. What is conditional probability tables? Conditional probability table is that it's a product of parents. For example, for the node C, we use the probability of the parents, that is S and M. That is the conditional probability table. We'll see why. The compact representation of a joint probability distribution. We see what is Bayesian network. Why the network is called compact? So in the previous slide, we saw how many probabilities we needed to represent the dynamic Bayesian network we created. So, okay, the Bayesian network. How many values we used? We used 2. We used 2, therefore, and here 2. Okay, there are like 10 particular values we used. Why we call this Bayesian network is compact? Can you think for a moment and pause this video, think about it and reflect on it, and then continue. In the Boolean values, the 4 nodes are given. We usually need 4 nodes given. We would need a fully connected network. It will need a 2 power 4 minus 1. Maybe it's a 15 particular values is needed. What is V given S? What is V given M? All those values is needed. But in our particular case, we used Bayesian network. Probability of sleeping, probability of meeting, probability of 4 times the the C naught, and probability of value equal to C. So there are 4 values given for us, like 8 values given for us. So we kind of reduce the representation from 16 to 15, sorry, 15 to 8. So that's why it's called compact. How it become compact? Because we created directionality and we avoided the acyclic graph. By doing this, the conditional probability has been reducing it. So why Bayesian, why the probability of S is equal to 1? It is just a probability of S equal to 0 or 1. Here the probability of C naught given 0, given S and M. We consider all 1 value, then we kind of computed it. So we need opposite, if you want C equal to 0 given SNM, then we need a 1 minus that value. That is why I said 8 probability is enough to represent this whole network. Okay. So compact representation of joint distribution of overall variables in network is called Bayesian network. It's called compact because the directed acyclic graph reduces the 2 power, the number of nodes minus 1 into a set of less number of conditional dependencies. So this is called conditional probability table, this particular values this. We'll see that in an example. For example, a student have to read two explanations, and the concept will be understood by reading this explanation. If the concept is understood, the student would answer two questions, 1 and 2. Let's go in detail here in this. This is a concept. Maybe the concept can be, say the concept is fractions. And to understand the concept, we give two type of explanations. Okay, the explanation is given to the students. They can read explanation A, explanation B. What is the student's prior knowledge of having explanation A is 0.01. Student having the prior knowledge of explanation is 0.02, which means there is no very least a very low probability that student might have known this explanation before. Okay. Based on the lot of data, historical data, we conducted the study with hundreds of students, thousands of students. Based on the data, if the student read explanation A and read explanation B, their understanding of a concept is 0.95. It's high. Okay. If the student read explanation A but not explanation B, still they have a high knowledge on the concept, because explanation A has a lot of material covered for the concept C. If the student not read explanation A, only explanation B, the probability goes down. If the student did not read both explanation, the probability of knowing the concept is 0.00. So this node, explanation A, the prior knowledge is known. This is a known node. Okay, known value. Answer. We are trying to test the student's knowledge using set of questions. Two questions we are going to look at it. If the student knows the concept well, the student would answer the question correctly. Okay, student don't know the concept, the student answering the question is, there's a 0.05 possibility. If a student knows the concept well, the student could answer the A2 question with a very good 0.70% of probability, 0.7 probability. Here, which means the A2 is not only this concept, it may be adding bit more high concept. Even if you know the question, there is a chance that you may not answer it. If a student not knowing the concept, there's probability like 0.01, you could answer the question, because these are data from the existing values. We conducted this study to say 1,000 students, we collected the data, then we computed this probability table. Now, this concept C is hidden. It is the latent node. What happens? We know before coming to the particular system, students' prior knowledge and explanation, that is, knowledge of the concept is less, so that's a 0.00, 0.01 or 0.02 we gave. Now, this answer is also given. Now, my question is, given the answers to these two questions, what is the probability student know the concept C? That's what we are interested. Okay. So now we use the Bayes theorem. If you know that the students both answers 1 and answer 2 is known, given the answer, it can be yes or no, it can be right or wrong, what would be the probability of the later node that students knows the concept? We want to understand the student knowing the concept fraction, that is the mastery or the skill we want to measure. Okay, is it clear? That's the Bayesian network, the basic idea. So, in the previous example, that is the example we saw, which node we can update at every time based on student's response. Just pause the video. Based on the student's response, we want to update one particular node every time. Suppose I have 100 students data, 1,000 students data. Every time students data is increases, which node I need to update? The node concepts indicates whether the student understood the concept or not. Hence, we can update the conditional probability table of concept based on student response. Okay, if I have more students response, we can update the conditional probability table. So the conditional probability table of Bayesian network is a dynamic network. Updating this at every instance, it becomes a dynamic Bayesian network. You see, I said dynamic network is a state 1 to state 2. When the state changes, we update the conditional probability table of this particular system, then it becomes dynamic. I hope this is clear now. Now see another one. In a tutor called Anders tutor, it's one of the famous tutor. In Anders tutor for science concepts, students read a text on Newton's law, okay, then solves a problem on Newton's law. They read a test and solves a problem. How do you represent this knowledge using Bayesian network? So now we saw what is Bayesian network. We saw two examples: skipping the class, knowing the concept, given two explanation, two answers. Now here, student reads a test, then solves the problem. Can you draw a simple Bayesian network? Please pause this video and draw it, then play. So we could represent as a simple graph. In the previous one, we had a read test 1 and we have another test, then 2 questions. But here it's a simple problem. So it's applies like the based on the experts' knowledge. That's why it's called a belief network. Experts believe that if I read this test and if I solve this problem, my student will know Newton's law. This is the experts' belief. That's why it's a belief network, Bayesian belief network. So can we create a conditional probability table for this network? Condition all these values are Boolean. Yeah. If you create a conditional probability for the network, how many probability variables are required for the simple Bayesian network? Please pause this video, write down your answers, then continue. Let's go. I hope you have this similar answer. The idea is that conditional, if you consider only the positive values of variable nodes, okay, the reading test, okay, the probability of reading, the people read the test. If they read the test, probability of students knowing the thing could be computed, 0.9. If not read the test, probability of knowing may be 0.5 or something like that. Answering the problem, knowing the law, that's also maybe 0.9 maybe. Without reading the Newton's law, answering the problem, also possible with some kind of cases. So we could come up with these kind of values. So these are the conditional probability tables. Basically, these two values you will have to improve on it. Okay. Probability of the student already read the test can be very less. Such so we can keep it 0.03 or 0.5 or 0.1 or something like that. Okay. Now, given these two values, for example, I know the value of being Newton's law. If I read the Newton's law correct, I know the value will be 0.95. If I know the Newton's law, I did not read, getting the right answer, there's a chance that 0.2, maybe it's a MCQ, it's possible 20%, 20% chance is there. Assume that the initial probability the student know Newton's law is 0.5, which means probability of reading the initial thing is only 0.5, which means we don't know student know the idea or not, which means we had no idea whether student know a topic, so we assume 0.5. Compute the probability of A given B, that is, given the student passing the score problem 0.023, what is the probability that we can assume the student knows Newton's law? So I said that we have to apply the Bayes theorem. The question here is, given this, we observe the student has answered the question, we are going to assume the student knows the skill. Okay. Please pause this video, try to compute this problem, then after computing, continue to watch. So to continue, we use the same Bayesian's problem. So consider the case 1, the response is correct. Knowing the knowledge problem, given the problem will be 0.95, that is the value probability of answering the problem correct, knowing the KNL, right? The students on the 0.95 into 0.5 because that is a prior knowledge into the same score. Okay, this is a very simple Bayesian logic. Now, if the student answered the question correct, we will compute the student's mastery skill on students knowing Newton's law. I hope it is clear. So, this is how we compute the student's knowledge using the Bayesian network. Okay. For the value if it's 0, we would be able to compute the against applying the same logic, we would be able to compute the students knowing uh, the Newton's law will be like 0.006. I hope you understood what is Bayesian network, the directed acyclic graph, and what is a conditional probability table, and also you would have looked at how to use this Bayesian network to understand the student's mastery based on given set of responses to the particular questions. Thank you.